All right, and then we'll get started. So welcome back, everyone. Already halfway through the week of the school, which has been very interesting so far. And hopefully today we will have some new lectures, which will hopefully be equally interesting. I have full faith that that'll be the case. So before we start, let me make a few technical remarks. One you already know probably, but if you have subtitles on your screen and you're annoyed by them rather than helped, then you can always turn them off using this live transcript button. Secondly, a reminder that after today's lecture, there's again a tutorial, which will be in the same link as yesterday, so it'll be put in chat as well. So that's from 5 to 7 UK time today. If you're looking for slides, exercises, and so on, those can be found on the murals. And also a remark that you've all heard before, which is that, of course, questions can always be asked in the Q&A or in the chat, preferably in the Q&A. But also at the end, you can always raise your hand and you can ask a question in speech if you want. But remember that we are recording and live streaming this. So if you don't want to appear on the recording or on the live streaming, then you should use the Q&A to do so in writing. So that's all the technical remarks I had. Like I said, today we'll have 3 new lecturers. And in fact, the first new lecturer is 3 new lecturers as well, because Philippe, Trinh, John King, and John Chapman together are giving 3 lectures on exponential asymptotics for physical applications. I think John will be the one speaking today, or at least starting today.
Yeah, that's
correct. Okay, then by all means, go ahead, share your screen, and we'll enjoy what you have to say. And I'll give you a reminder at 55 that it's time to stop.
Okay, perfect. Yes, so Phil, John, and I are going to give these 3 lectures. We're going to give 1 each. I'm going to give the introductory lecture today on nonlinear ODEs. Then Phil is going to talk about water wave problems, and John is going to talk about multiple scales problems, I think. And this lecture follows on from the overview lecture I gave last week at the beginning of the program. That lecture was sort of a rapid, brief view at lots of different problems. And here today, I'm going to go into a bit more detail in for 1 or 2 problems for the nonlinear ODEs. Everything today is self-contained, so it doesn't matter if you didn't watch the last week's lecture, but you might find it interesting to do so for a bit of context. Okay, so I'm going to talk about mainly the methodology. I'm going to introduce it with linear ordinary differential equations, talk about Stokes phenomenon, singular perturbations and divergent series, Stokes line smoothing, and factorial over power ansatz for the late terms. I'm sure some of these things you're hearing about in the other lecture series in this program. So apologies if it's a bit repetitive, but everybody has a different sort of take on these things, so it is useful to have to see them again in context. And then I'm going to apply that methodology to a particular example of nonlinear eigenvalue problem, which is the Kruskal-Seeger crystal growth problem. So Stokes phenomenon, it's impossible to do anything with exponential asymptotics without coming across Stokes phenomenon. So let me just remind you about it. Traditionally, you first encounter it normally when you're looking at approximations of integrals. So here I have the integral expression for the error function, the complementary error function. And typically you're interested in asymptotic approximation for the error function for large values of this argument Z. And if you're doing that via steepest descent, then you would deform this contour in the complex plane. So if Z is complex to the steepest descent contour and approximate it by, you'd get an endpoint contribution from this endpoint z. So this is sort of a picture of this integral. This is the real part of t. This is the imaginary part of t, thinking of t in the complex plane. This is the endpoint z, which is on the positive real axis at the moment. And this integral goes from that, the black line shows you the contour going from z to infinity. And what happens as you move z around in the complex plane, you find that the steepest descent contour from this endpoint, so the quickest way to go downhill from that endpoint z, if z is in the right half plane, then that goes to plus infinity as you want. But if z is in the left half plane, then the steepest descent contour goes off to minus infinity. And in order to get back to plus infinity, where the second endpoint of the integral is, I have to add this integration on the real axis over this saddle point. So as z crosses the imaginary axis, you get a change in the topology of the steepest descent contour. And that corresponds to getting not just an endpoint contribution, but also a saddle point contribution due to this extra integration. So you have an extra term due to this extra contour, which is only present for some values of z and not for others. And the relative size of these two contributions is determined by the relative height of the saddle point and the endpoint. And you can see that as the endpoint crosses the imaginary axis, it's higher than the saddle. And so the new contribution is exponentially small when it's turned on, but you need to know it's there because for some values of z, it's the dominant contribution. And a lot of exponential asymptotics is to do with identifying these exponentially small terms as they're switched on that lie beyond all orders of an asymptotic series. And if you didn't know that they were there, then you'd get completely the wrong answer in other parts of the complex plane. So Stokes phenomenon is all to do with this, the two processes of analytic continuation, so as I move z around in the complex plane, and asymptotic expansion. Okay, the complementary error functions, it's a nice example where you see the change in topology of the contour. But I want to choose a slightly simpler example in order to illustrate the concept of Stokes lines and Stokes line smoothing. And that simpler example is the exponential integral. And already I'm going to switch to differential equations rather than integrals here. So I've got this first order linear differential equation with a small parameter epsilon. So before I was doing what you might call a coordinate expansion, I was approximating the error function for large values of z. In general, we will have a small parameter in an equation rather than a large coordinate. So I've just rescaled here. I rescaled z with 1 over epsilon. And so that just gives me a small parameter epsilon in the equation. I can do exactly the same thing with this, now letting epsilon tend to 0 instead of z tend to infinity. So if I use an integrating factor on this differential equation, I can write an integral expression for f, and then I could just do steepest descent. Here you see explicitly that as epsilon goes to 0, the argument here goes to, the argument goes to infinity. So the steepest descent on this integral is sort of trivial, that the landscape, the energy landscape, is just a flat plane. E to the t grows linearly. The argument t grows linearly. The real part grows linearly in the real part of t here. So the steepest descent contour is just parallel to the real axis and goes off to minus infinity in this case. So here I'm starting on the negative real axis. And if I do the same thing and swing around in the complex plane, you can see that as the endpoint here crosses the positive real axis, the steepest descent contour crosses the pole here, which is represented by this spike here. And so you're going to get this extra contribution from this pole as you cross the positive real axis. The endpoint contribution, that's just the you can integrate by parts to find the asymptotic expansion of f as epsilon tends to 0, and you get a power series expansion in epsilon and inverse powers of z. And this time the extra contribution that you switch on is just the pole contribution, so the residue here is 1, so I get just e to the minus z over epsilon times 2 pi I is switched on as I cross the real axis. So this is present for whenever the argument of z is positive when I'm in the upper half plane, but it's not present when I'm in the lower half plane. So if I was to write down what the asymptotic expansion of f is, if I start here on the negative real axis, I've got this power series expansion in powers of epsilon. As I move around here, I cross the positive real axis and I pick up this exponentially small term, which lies beyond all orders of this power series. So it's smaller than any power epsilon to the n. But as I cross the imaginary axis, this exponentially small term becomes exponentially large once the real part of z is negative. So it jumps all these orders and jumps to the front of this series. So you need to know that it's there, because if you didn't know that it was there, this approximation here, there's no indication that this approximation is breaking down, but it's completely wrong by the time you get to this point, this quadrant. So you need to know that this term has been switched on across this Stokes line. Okay, so what could you do if you didn't have an integral representation? Well, it's very easy from this, this differential equation just to do a formal expansion in powers of epsilon. If I propose such an expansion, substitute it into the equation, and then just equate coefficients of powers of epsilon, I'm going to find that the first term in this expansion is just 1 over z. And then to get the next term, I just differentiate the previous term. And that allows you to generate the whole, the full expansion very easily. You find that differentiate 1 over z, I get 1 over z squared, and then 2 over z cubed, and the general term is just n minus 1 factorial over z to the n. So you get this factorial over power behavior that is typical of singular perturbation problems. So this is an asymptotic expansion. Each term is a factor of epsilon smaller than the one before. And so if epsilon is small, then the terms are gradually getting smaller and smaller, as is true of all asymptotic expansions. But if I take n sufficiently large, then the factorial here, the n minus 1 factorial, beats the epsilon. So eventually, if n is large enough, these terms will get bigger again. And so, in fact, this series is divergent. It diverges for all z. And it's that divergence that's a sign that there's an exponential lurking behind it. So if I want a good approximation, I need to truncate this asymptotic expansion. So let me truncate it after n terms and study what happens for the remainder. If I do that at any fixed n, then the remainder is order epsilon to the n. That's what it means for this expansion to be an asymptotic expansion. But if I let n depend on epsilon, so I truncate optimally at this point here, then it turns out the remainder Rn is exponentially small. And that allows you to see the hidden exponential behind the infinite series of powers. So where is this optimal truncation point? The ratio between successive terms in this expansion, so to get the next term, I multiply by n, I multiply by epsilon, and I divide by z. And so the least term occurs where this expression is about 1, and that's because the two terms at the bottom here of this U shape have roughly the same size. And so at the minimum here, successive terms have got the same modulus. So that tells me the optimal truncation point is about n as mod z over epsilon. So let me truncate at that point and look to see what happens to the remainder. So if you do that, you find that you can write down the explicit equation for the remainder in this case. And I have this n factorial over z epsilon to the n over z to the n on the right-hand side here. So I want to try and solve this equation for Rn now. And to do so, I'm going to first write z in terms of modulus and a phase. So I'll write z as Re to the I theta. And the optimal truncation point then depends on mod z. So it's just n as R over epsilon. But n better be an integer. So I'm going to add an alpha to that in order to make this an integer. But alpha is going to be bounded as epsilon tends to 0. Or R over epsilon tends to infinity. For the factorial, I'm going to use Stirling's formula because I'm doing this for epsilon is small, so n is large. And so for this term on the right-hand side here, you put the factorial in, you put the z as Re to the I theta in, and then you start manipulating it. So if I then put what this optimal truncation point is in for n there, then you find when the dust settles, you get an expression that looks like this. So you find that it is indeed exponentially small as epsilon tends to 0. And that effectively arises from Stirling's formula here, from the e to the minus n here. Okay. We can go further. So the remainder is exponentially small. If I now say that I look at the homogeneous version of that equation, then I know it has solutions which are e to the minus z over epsilon. And so I'm going to write the remainder to be some function of z, s of z, times this solution of the homogeneous problem, where s is known as the Stokes multiplier. So that's just a change of the dependent variable. If I substitute that into the equation, then you find that, so epsilon drn by dz plus rn just becomes an epsilon e to the minus z over epsilon times ds by dz. So this gives me this equation now for ds by dz. And now, so I want to write this ds by dz, I could write that in terms of d by dr or d by d theta. Z is a complex variable, and I choose to write it in terms of d by d theta because n is a function of r, but it doesn't depend on theta. So I really am swinging around in a circle in the complex plane. I'm going to keep r constant, and I'm going to vary theta. So little application of the chain rule tells me what d by dz is in terms of d by d theta. And so I can write this whole expression here as ds by d theta is equal to some expression where I also replace the e to the minus z over epsilon here. So that becomes an e to the plus z over epsilon on this side. And then z is re to the I theta over epsilon. So we see, in fact, that s is also exponentially small. I've factored out an exponential, but it's still exponentially small almost everywhere. So I've still got an e to the minus r over epsilon here, but I've also got an e to the r plus r over epsilon here, but it's got an e to the I theta here. And the real part of e to the I theta is less than 1 unless theta is 0. So if theta is non-zero, this term is exponentially small. But if theta is exactly 0, these two terms cancel here. And then you find that actually ds by d theta is not small, it's large because I've got a 1 over epsilon to the half out the front. So I have this situation where the Stokes multiplier is exponentially small except, the derivative of the Stokes multiplier is exponentially small except where theta is 0. And when theta is 0, you find that it's algebraically large. And so whenever you've got a function that's the derivative is small, but then suddenly it's large in the vicinity of a particular point, that tells you I've got a boundary layer type problem. And I can solve such an equation via matched asymptotic expansions. So in order to do so, I need to scale theta and look locally in the vicinity of the boundary layer, which is at theta is equal to 0. So I'm going to introduce a scaling, I'm going to suppose that I don't know how big the boundary layer is. So I've got this arbitrary scale delta, and I'm going to choose delta in order to get a sensible balance when the time comes. So I scale theta to be delta theta bar, where delta is small, but I'm not quite sure yet how small. And then, so what's going to happen when theta goes to 0? Well, I've got to expand, substitute this in and expand now in powers of delta. And so I do that just by looking at the Taylor expansion of this term here as the crucial term. And you can see that when I do that expansion, I'm going to get e to the r over epsilon, which is going to cancel with this term here. I'm going to get an e to the I theta r over epsilon, which is going to cancel with this term here. And so the term that's going to be left is this e to the minus theta squared r over 2 epsilon. So when you substitute this change of variable for theta into the equation, you get a ds by d theta bar is equal to this thing here. And now I have to choose delta in order to make this a sensible balance. And you can see that I've got a delta squared on the top and I've got an epsilon on the bottom here. So the right scale to choose is where delta squared is order epsilon. So delta is equal to epsilon to the half. That tells you the thickness of the boundary layer, the thickness of the region in which the Stokes transition happens. So if I put delta as epsilon to the half, I get ds by d theta is e to the minus theta bar squared with a few constants. And I can integrate that up and I find that the Stokes multiplier is in fact an error function. I know that as s tends to minus infinity, sorry, as theta tends to minus infinity or s tends to 0, there is no exponential if I'm on one side of the Stokes line. And then as theta bar tends to plus infinity, as I go out of the boundary layer on the other side, I can see that s tends to a constant, and the constant it tends to is just this full integral here, which is 2 pi I. So the boundary layer solution is a smooth error function transition where s goes from 0 to 2 pi I. And so if I match that with the outer solution away from the Stokes line, you find that the outer solution effectively sees a jump, and the jump in the Stokes multiplier is 2 pi I. So this shows you that you can explicitly see the turning on of this 2 pi I over epsilon, 2 pi I e to the minus z over epsilon as you cross the Stokes line. And this is the famous error function smoothing at the Stokes discontinuity that Mike Berry wrote about in 1989, sort of reinterpreted in terms of matched asymptotic expansions. So what are the messages to take away from that calculation? Well, so the Stokes line occurred where successive terms in the asymptotic expansion had the same phase. So the ratio of successive terms was real and positive. So in this case, Z is real and positive. That's an observation that goes back to Dingle. Along with that, on the Stokes line, the phase of the dominant and subdominant exponentials is the same. And that means that the dominant exponential is maximally dominant. So here the two exponentials are e to the z over epsilon and 1, and they've got the same phase where z is real and positive. And the most important thing is that in order to find the Stokes multiplier and identify the Stokes line, I did not need to know much about the early terms in the series. All I needed to know was the behavior of Fn, the asymptotic expansion in powers of epsilon, as n tended to infinity, because the optimal truncation point is was n is 1 over epsilon. So I only needed to know about the behavior of the series for large n. And that means you can use the same sort of idea, approximating the late terms, smoothing the Stokes line to identify Stokes multipliers on many more types of problems. And so the formal procedure would be to formally expand in power series in powers of epsilon. I want to know what the late terms in that series are, and I know they're going to diverge as factorial of a power if my problem is a singular perturbation problem. So I'm going to make that ansatz. I'm going to assume I get a factorial of a power divergence and see if I can work out what the power is, what the singulant chi is, and what the amplitude A is. I know the singularities of this function must be the same as the singularities of the leading order problem, because every problem after the first was linear, and the linear problem cannot introduce any new singularities. And so I know the singularities of phi n must be the same as the singularities of phi 0, and therefore this singulant chi must vanish at one of the singularities of phi 0. When I do this ansatz, there are going to be a couple of unknown constants. One is this parameter gamma you can see here, and the other is a constant scalar factor in A. And those I'll need to identify by, again, doing a bit of matched asymptotic expansions with an inner region in the vicinity of each singularity. I'll show you how that works in a particular problem. And then having found this form for the late terms, I can do the Stokes line smoothing and identify that where chi is real and positive, successive terms have the same phase, there will be a Stokes line, and you can almost read off what's going to be turned on across that Stokes line, because the Stokes smoothing calculation is universal. You get more or less the same behavior every time. Okay, let me show you how that works for a nonlinear eigenvalue problem. So this is one of the problems that sort of kicked off the theory of exponential asymptotics beyond all orders in applied mathematics in nonlinear ordinary differential equations. And it's a toy model for crystal growth, where you imagine this is a needle crystal and it's traveling with unit speed. So I'm looking for a traveling wave solution. And the law of motion is that the normal velocity is equal to the curvature plus some small perturbation times the second derivative of curvature with respect to arc length. Now, I'm not really sure why somebody wrote down this law of motion. I don't know whether this is supposed to represent some sort of surface diffusion, would be my guess. But as I say, it is a problem people have looked at as a toy model. The easiest way to describe the shape of this finger is to use the angle that the normal makes with the x-axis, which is the direction of propagation. Because if you do that, then the curvature is just the derivative of phi with respect to arc length. And the normal velocity, I just take the component of the normal in the x direction. So this equation very simply then just translates to this nonlinear ordinary differential equation. And if I'm looking for a needle finger solution, I want phi to tend to minus pi over 2 at this end and plus pi over 2 at this end. So this is the problem that I want to solve. If you put epsilon at 0, then you can solve this problem. It's a simple first order separable differential equation. You can write down the exact solution. And in fact, if you do a power series expansion, it'll go up in powers of epsilon squared, because there's an epsilon squared here. You find that you can satisfy the equation and boundary conditions at every order. But in fact, and here's what this is what phi 0 looks like as a function of arc length, and this is the shape that you get for the needle. So everything seems very sensible. But you can tell that something's not quite right if you just if you linearize about the far field behavior. So at this point where phi goes to minus pi over 2 and s goes to minus infinity. So if I linearize the equation about that point, I get this equation for the perturbation, the way that phi approaches minus pi over 2. And so it's simple constant coefficient linear differential equation. So you got exponentials as solutions, and you get 3 exponentials, one of which is real and the other 2 are complex conjugates. But as s tends to minus infinity, only the e to the s here decays, but the e to the minus s over 2 grows. So there are 3 arbitrary constants here, but if I say that phi goes to minus pi over 2, as s goes to minus infinity, that kills 2 degrees of freedom. It says that beta and gamma should both be 0. So effectively, that far field behavior is 2 boundary conditions because it's killing 2 degrees of freedom. And if you look at the behavior as phi tends to plus pi over 2, as s goes to plus infinity, you find that also kills 2 degrees of freedom. So it's also 2 boundary conditions. And so by looking for such a solution, I'm effectively imposing 4 boundary conditions on this 3rd order differential equation. And so I would not expect to find a solution. In fact, it's worse than that because the equation is translationally invariant. And so I would have an extra boundary condition in order to fix the origin of S. So you would have to be incredibly lucky if you did have a solution to the problem. And in fact, you're not lucky. You can prove that there's no solution. So what is going on? If a solution did exist, then you could fix the origin so that it was anti-symmetric. So if I then, suppose I solve the equation where I give you that phi goes to minus pi over 2 as s goes to minus infinity, but instead of going all the way to plus infinity, I stop at the origin and I say that phi of 0 is equal to 0. So that's now the right number of boundary conditions. It's a 3rd order equation. I've given 1 condition at the origin and 2 at minus infinity. So it's correctly specified problem. And you will find that you get an anti-symmetric solution to the original problem if and only if the 2nd derivative of the origin turns out to be 0 when I solve this problem. And what you find is that the 2nd derivative at the origin is not 0, but it's exponentially small in epsilon as epsilon tends to 0. And it's the fact that this is exponentially small, that's the reason that the asymptotic expansion in powers of epsilon could not pick it up. If you just do an asymptotic expansion in powers of epsilon, effectively you find this is 0 at every order in that expansion, and so it looks like you have a finger solution. But in fact, you don't, because this 2nd derivative is exponentially small. All right, how do I show you that this is the case? Let's do our optimal truncation and the formal procedure that I laid out. So I'm going to do it with an f of phi on the right-hand side here, because you can do it in some generality, but if we're going to use f as cos phi at the end of the day. Okay, so what's the procedure? I formally expand in powers of epsilon. So I'm going to generate a power series expansion. It's going to go in epsilon to the epsilon squared, so that the nth term is epsilon to the 2n times phi n. So I substitute that in. You can see at leading order, this term drops out, so you just get phi prime is f of phi. At 1st order, you have phi 1 prime is, I've got to Taylor expand this term when I substitute this in, so I'm going to get an f prime of phi naught there, and then this term is going to start appearing. This is equating coefficients of epsilon squared here. And then in general, I'm going to get a phi n minus 1 from this term and a phi n from this term when I'm equating coefficient of epsilon to the 2n. And I'm going to get a whole load of junk on the right-hand side here from doing a Taylor expansion of f, which is where the argument is also a power series expansion. So you're going to get terms that you get from the quadratic terms in the middle and the 2nd derivative, and then you're going to find all the ones from the 3rd derivative. So it's going to be a whole mess in general here. And so generating the full asymptotic expansion here is hard. It's usually very easy to get the 1st term. With a bit of work, you can get the next term. To get the 2nd or 3rd or 4th term is getting progressively harder and harder and harder, and getting algebraically much, much, much more complicated. But fortunately, I don't need to find the 2nd or 3rd or 4th term. What I need is the leading term in order to know where the singularity is. And I need the nth term where n is large. And in this case, it's much easier to find the large n behavior than it is to find the low order terms in the asymptotic series. So to get the exponential accuracy in phi, I'm going to truncate optimally. So I need to know how phi n behaves as n tends to infinity. The singular points of phi n are the same as those of phi n minus 1. But if I have some singularity in phi n minus 1, when I generate phi n, I have to differentiate that twice. And so s to the minus p ends up being a p plus 1 times s to the minus p plus 2. Again, it's a singular perturbation problem, so you end up getting factorial over power divergence. So let me make that ansatz. I'm going to assume that I've got phi n as diverging like a factorial over power. Now, so in my general procedure, I just wrote gamma of n plus gamma over chi to the n plus gamma. Here I've put 2n in, and that's because I know that I'm differentiating twice. And so if I had an s to the minus p, I'm getting a p plus 1. I'm going 2 steps down the factorial for every term in the expansion. So this ansatz is very similar to a WKB ansatz with a phase and an amplitude. So the singulant chi is playing the role of the phase. If I substitute this ansatz into the equation, here I'm just showing you how big each of the terms roughly is. So phi n minus 1. So n minus 1 means that I'm 2 orders down in the factorial here, so it would be 2n plus gamma minus 2, but then I differentiate 3 times, and each one gives me a factor of n, so that's going to give me 2n plus gamma plus 1 in the end. And the phi n prime in the equation, well, I just differentiate once, so I go from 2n plus gamma to 2n plus gamma plus 1. On the right-hand side, I had a phi n times f prime of phi 0, so that's just a gamma to the 2n plus gamma. And then I've got all the junk, and in general, lots of junk down here. But each term is getting smaller and smaller, because this one, the phi 1 is sort of irrelevant. What matters is the phi n's here. And this is a phi n minus 1, and already phi n minus 1 is 2n plus gamma minus 2. So whatever this term is, it's a factor of n squared smaller than this term. And then the next one down would have a phi of n minus 2, and that's going to be a factor of n squared smaller again. So even though you get a whole mess here when you do this expansion, you really only need this term in order to work out what's going on in this factorial over power ansatz. Okay, so here is my general equation for phi n, and here I've just written down what this is my ansatz for phi n. This is what phi n prime is going to look like. I'm going to get a chi prime, and I'm going to get an extra chi on the bottom from the chain rule, and differentiating this 1 over chi to the 2n plus gamma. And then for chi 3 prime with an n minus 1, I'm differentiating 3 times, but I'm interested in, the factors of n that I pick up, and I get a factor of n every time I differentiate the 1 over chi to the 2n. So that's why the leading term in this is going to be the chi prime cubed here. And then there'll be other terms that you get from differentiating the amplitude and the chi again. So I've sort of color-coded how big these terms are. These 2 terms are gamma to the 2n plus gamma plus 1, and then these 3 terms are all gamma to the 2n plus gamma. So when you substitute them into the equation, the leading order balance you get is just between these 2 terms at the front, and it's these 2 terms in purple here. When you balance those, you find you get just the iconal equation for this singulant chi. And in this particular case, it's a very simple equation that just gives me constant solutions. So chi is plus or minus I. Changing the sign of chi because I'm squaring it here, all that does is change the amplitude by a constant factor. So without loss of generality, I can just choose the positive sign here. The singular points of phi n, as I said, must be the same as the singular points of phi 0. So let me assume that I've got a number of those, and I'm going to index them by k and call them sigma k. So I know that for one of these singular points, this series should be such that the singulant vanishes, so that the singularity of phi n is the same as one of the singularities of phi 0. So I can just read off what the singulant has to be. And in general, you will have a factorial over power behavior like this, one term like this, for every singularity in the leading order solution. So I would have a sum of series that look like this. But for large n, the ones that dominate are going to be the ones with the smallest value of chi, and that means the smallest value of the modulus of s minus sigma k, and that means the singularities that are closest to the real axis. What about the next term, the amplitude equation? So if I then equate these three terms in this expression, you get an equation for A, and turns out you can integrate that equation up and just write A in terms of the leading order solution. So we have been able to find the expression for the late terms explicitly in terms of the leading order solution and its singularities up to two constants. So I haven't yet told you how to fix this offset in the factorial, this gamma. And then also when I solved the amplitude equation, it was a linear equation. So I've got an arbitrary scalar factor, lambda out the front, and I would have one of those for each of the singularities. Okay, I'm going to tell you what to do about lambda later. Often it's not so important what it is, it's only important that it's non-zero. But there are techniques for finding it if you really want to know it. The gamma here is in some sense more important, but also easier to find. So to determine the gamma, you just got to make sure that the singularity in phi n is consistent with that in phi 0. And effectively, what that means is that if I just look at, if I put n as 0 in here, I want the order of the singularity to be the right. So that seems a little bit perverse that I said this is the large n asymptotic approximation to phi n, and then I'm going to put n as 0. I'm not claiming that this is a sensible approximation to phi when n is 0. What I'm claiming is that because the order of the singularity is going up by 2 every time, in order to have the right order of the pole for large n, I have to make sure that I have the right order when I put n is 0 in here. And so to do that, all I do is I compare what I would get if I put n as 0 in here to what I know from the leading order solution. So suppose the leading order solution has behavior as s tends to sigma, which is s minus sigma to the beta. Then I need s minus sigma to the beta to be, so what would I get if I put n as 0 up here? Well, I'd get an s minus sigma to the gamma on the bottom here. And then actually, I've got to be careful about this phi prime to the half. So phi prime to the half would give me this beta minus 1 over 2 term as well. So if I make sure the powers of s minus sigma are consistent on the right and the left here, I can read off exactly what the gamma is in terms of the beta. So the only unknown we've got left is the lambda, and I'm going to come back to that later. Okay, we treat the factorial over power generated by each singularity separately. In order for there to be a Stokes line, successive terms have to have the same phase. So that means that chi squared is real and positive. I'm just going to run through the calculation to show you that it's actually, the Stokes line smoothing is universal. So if I truncate after n terms, then I get an equation for the remainder, which is, it's got the linearized operator on the left-hand side, and then it's got a whole mess of stuff on the right-hand side. But I'm only interested in what this inhomogeneous term is in the limit of large n. And I know that this term is generated by the fact that effectively this term was missing when I truncate this series. The easiest way I find to work out actually what I should put on the right-hand side here is that if I hadn't truncated, then what I would be getting is the next term in the expansion is phi n, phi capital N. So Rn should look like phi capital N if I hadn't truncated. And so I just put phi capital N into wherever Rn is here, and that tells me what I should get here. So what I should get is epsilon to the 2n times phi capital N prime. There would be this term as well, but this is lower order as n tends to infinity because I get a factor of n when I differentiate. Okay, so there's the remainder equation, and homogeneous version of that equation is it's third order, so it has three solutions, three possible complementary functions. Because the original problem was translation invariant, I can always find a solution which would just be the derivative of the leading order solution. The ones I'm interested in are the two exponentials, and this is the one which is going to be turned on here. So I'm going to look for a multiple of e to the minus is over epsilon. So you do the same steps. You switch to the polar representation. So the relevant variable here is chi, so that's is minus sigma. I look at the optimal truncation point. I choose n to be close to that. It needs to be an integer, so I better add alpha, but alpha is bounded. I define the Stokes multiplier to be some multiple of the solution of the homogeneous remainder equation. I switch d by ds into d by d theta, and I use the factorial of a power ansatz to approximate the inhomogeneous term on the right-hand side of the equation, along with Stirling's formula for the factorial. And if you do all that, then you find you get this equation for the Stokes multiplier, which again is exponentially small, except in the neighborhood of theta is 0. So you do the same scaling in the boundary layer, you do the same Taylor expansion, you find that you get the same width of the Stokes line. In this case, I get a delta squared over epsilon, so I know that again delta is order root epsilon. I see that the Stokes multiplier, there's still an epsilon to the gamma here. So the Stokes multiplier is order 1 over epsilon to the gamma. And when you put those scalings in, you find you just get an error function back again. And you can work out by effectively integrating from minus infinity to infinity here and matching with the solution away from the Stokes line, you can work out what the jump in this Stokes multiplier is as theta crosses 0, as it goes from 0 minus to 0 plus. And in this case, it's 2 times lambda times pi times I, and then there's this factor epsilon to the gamma here. So this is almost what I said before. I'm missing a 2. The epsilon to the gamma is just because the 1 over chi to the 2n plus gamma I have on the bottom, I had an epsilon to the 2n on the top. So that's just to get those two things to match up. The reason I lose 2 here is because the expansion was going up as gamma to the 2n instead of gamma to the n. All right, what are the implications for the Kruskal-Seeger problem? So I had logarithmic singularities in my leading order solution. So logarithmic singularities corresponds to beta is 0. So if I read that off, that tells me gamma is 2. Since the derivative of the leading order solution is just a sec, I can write down what the late terms are. And I got 2 contributions, one from the singularity at I pi over 2 and one from the singularity at minus I pi over 2. So there's a Stokes line down the imaginary axis from this one, across which this thing is turned on. And there's a Stokes line up the imaginary axis from this one, across which this is turned on. Since I know the solution is real on the real axis, I know that what's turned on here must be the conjugate of what's turned on here. On the real axis, the two exponentials are comparable. And so as you cross S is equal to 0 on the real axis, this is the thing which is turned on, where the R and the phi here are just related to this unknown coefficient lambda. So this is exponentially small, like e to the minus pi over 2 epsilon, rapidly oscillating, but it's exponentially growing at infinity. It's got a cosh S to the half. And that tells me this, this exponentially small contribution does not satisfy the boundary condition in infinity. So I don't have a solution. What would happen is that the naive expansion ceases to be valid when this term becomes order 1. So that when S is order 1 over epsilon, the e to the S over 2 here starts to become comparable to the e to the minus pi over 2 epsilon here. And I would cross the anti-Stokes line where at S is equal to pi, where this thing would actually balance with this. What about if I do it the other way? If I say phi of 0 is equal to 0 and I evaluate the second derivative at the origin? Well, so the exponential that I'm turning on, if I evaluate it exactly on the Stokes line at S is 0, I find I get an exponentially small contribution. You get a factor of a half because you're exactly halfway through the Stokes line. The cosh S is evaluated at 0 and the sine is evaluated at S is 0. So this is not quite 0. I'm supposed to solve with phi of 0 is 0. So I need to add a small multiple of the other complementary function to the remainder equation, which just corresponds to translational invariance. Having done that, if I evaluate the second derivative, this term actually doesn't contribute very much to the second derivative at all, because every time I differentiate this thing, I get a factor of 1 over epsilon. So this thing is going to dominate the expression for the second derivative at the origin. And that's where this formula that I showed you before comes from. It's from differentiating this twice. I had an epsilon to the half already. I pick up 2 more 1 over epsilons from differentiating twice, and I've got an e to the minus pi over 2 epsilon out the front. You can do the same thing with other potentials. If you have the Kuramoto-Sivashinsky equation, it just means your leading order solution is now tanh S. It's got simple poles, so beta is -1. That tells you gamma is 2. Qualitatively, the structure is exactly the same. You have 2 dominant behaviors in the late terms corresponding to S is I pi over 2 and S is minus I pi over 2. Something is turned on across a Stokes line down the imaginary axis from this one, and there's the conjugate is turned on from a Stokes line up the imaginary axis from this one. On the real axis, you find you have an exponentially small oscillatory term turned on, but it's exponentially growing at infinity again. So again, you find it's no solution. You might be tempted to think there's always no solution, but it's only the case in those 2 problems because the Stokes line was exactly on the imaginary axis. So if you switch to this form of F, which corresponds to some sort of anisotropy in the crystal growth, then the leading order solution is a bit harder now, but you find that you get 4 square root singularities, 1 in each quadrant. So you have sigma, sigma minus sigma, sigma bar, and minus sigma bar. So you get 2 Stokes lines. Again, they go down the imaginary axis from the ones in the upper half plane and up the imaginary axis from the ones in the lower half plane. So you have a Stokes line between these 2 across which one thing is turned on, and a Stokes line between these 2 across which a different multiple of the same thing is turned on, and that's crucial. So the amplitudes here are exactly the same, and so if the phases were exactly opposite, then I could get these 2 things to cancel so that I would have no multiple of this thing as I go off to infinity, and I would in fact find a solution to the problem. And so you can arrange for epsilon to be such that these 2 things are exactly out of phase, and if that's true, and so you get a discrete set of values of epsilon for which you get a solution to the problem, corresponding to basically having 1 wave or 2 waves or 3 waves in this sinusoidal oscillation in between the 2 Stokes lines. Okay. I promised I'd show you the procedure for determining this constant lambda in my last 2 minutes. So I'm going to do it for Kuramoto-Sivashinsky, which is slightly simpler. So I have my leading order solution, and I have it's got a simple pole as s tends to I pi over 2. So that tells me that there's some inner region in the vicinity of this singularity. So if I go locally near that singularity, I say s is I pi over 2 plus epsilon zeta. So zeta is going to be my local variable. Phi is growing like it's 1 over s minus I pi over 2. So if so phi is going to be order 1 over epsilon by the time I've got this close. So I should rescale phi as well. Then that gives you this inner equation for psi instead of phi, where prime here is d by d zeta. And so this has changed the balance in the equation. Originally, the epsilon squared was in front of this third derivative. It's not a singular perturbation problem anymore. You can do another expansion of this equation now in powers of epsilon. And what I would need to do is to match this expansion with the one I get from the far field. And the way to do that is, so I'm interested in what this expansion looks like for large zeta. So I do a power series expansion of this equation for inverse powers of zeta. And that just gives me a simple nonlinear recurrence relation to solve for the coefficients here. So that you can just give to a computer very easily. And then you just match those two expansions together. So the inner limit of the outer expansion has got my unknown coefficient lambda with a 1 over zeta to the 2n plus 1. And the inner expansion I've just expanded in terms of 1 over zeta to the 2n plus 1. So I just got to make sure these two coefficients agree for large values of n, which is when this expression is valid. And so I can just read off that this coefficient lambda should be the limit as n tends to infinity of an over gamma to the 2n plus 2. So you can find this lambda typically in terms of some nonlinear recurrence relation that you need to iterate. Okay, I'm done. Let me just put the formal procedure back up. But I'm happy to stop there and take questions.
Thank you, John, for a very nice talk. There were 2 questions in the chat, so let's start with those. One was about the very first example you showed, where you showed that this Stokes multiplier is described by the error, or the jump in it is described by the error function. And the question is, the connection formula is derived using Stirling's formula in some approximation. So it looks that it's not exact, but in an approximated form. Is that correct?
I guess well, of course, we know that that particular example is exact, but I guess it is. I never really thought about that. I guess it is an approximation. Chris Howells would have a few things to say about that, in the sense that he has various techniques where you know the thing you're looking for is an integer. So once you get within 0.5, you know you've got it exactly. But I guess in the way I presented it, it is you are approximating that right-hand side for large values of n. And so I guess, well, so it depends what you mean. I guess I get the leading term in the expansion exactly, and the question is, are there other terms that could be possible? And I guess that could be true. So I think that the 2 pi is exact as the leading term. I'm not sure whether it makes sense that there are higher terms in terms of what's the expansion parameter, but
might be a good exercise for the tutorial.
It might be a good exercise for the tutorial. I mean, you get into sort of hyperasymptotics and things at some stage when you go down that route.
Okay, thanks.
Yeah, sorry, it's not the clearest answer. It's something for the tutorial.
Yes. The other question was a bit later on, where you studied this large order behavior and you computed at some point gamma, which was an expression in terms of beta.
Yep.
So the question is, in your matching there, you compared large order behavior with phi 0. Can you explain again why this matching is appropriate?
So it's really just to make it, is to make the power of the singularity consistent. So if I know that the power of the leading singularity is a half, say, then I know that and I'm differentiating twice each, so it's going up by 2 each time. Then I know that for the first order problem, it's going to be a half plus 2. It's going to be 5 over 2. And for the second order problem, it's going to be a half plus 2 plus 2. So it's going to be 9 over 2. And I know for the nth order problem, it's going to be 2n plus 2 then, 2n plus a half. And so in order to make sure I've got the right offset in the end, I just need to say, well, what would the offset be if I put n is equal to 0? I hope that makes sense.
Yeah,
yep.
I think so. If not, Daniel. Oh, he asked something. Is this a heuristic argument? Or can the consistency not only arise in a large n limit?
It's a sort of, I mean, maybe this is something, again, for the tutorial to discuss, but I see it as almost a common sense sort of thing. If I'm going, if I'm increasing my order of my singularity by, suppose I'm increasing it by 1 every time, and I know that it was a half when I started off, I know it must be n plus a half after n times. That's
okay.
So I think it is a, a formal, there is a formal argument there, but the easy way to work out what it is to just put n is equal to 0.
Okay, thank you. I think we need to move on and maybe also have a little bit of a break. So let's give everyone 3 minutes to get a cup of coffee or have a short bathroom break.